All right, so remember we're looking at planar systems. So we have X and Y, right? First order, first derivative, and autonomous, right-hand side, time invariant. So no t, time independent, okay? Solutions look like this, right? Or like this, and that trace out curves, which are also called orbits or trajectories in the phase plane, which is the XY plane. And in the previous section, we did integral methods. All right, so we did stationary solutions, remember, and you solve this, and the way you do this is you set this equal to 0, right? That's how you do this. And you want to follow the logical thread, and I was very careful. And remember, the orbit of a stationary solution was just 1 point. Then the next thing you do is semi-stationary, if you remember all of this. But the key idea is you can go ahead and take, the semi-stationary solution. Its orbit lays on this, and then you transfer your phase line portrait to your phase plane portrait. And, same thing here, right? The orbit lays on this line, and then you transfer it to the phase plane. Okay. And you can go back, and it's just a good review to look at this. And then we did non-stationary, and I wrote down the orbit equation. And then we talked about the orbit equation being exact, right? And then the system's Hamiltonian. Or if it's not exact, you try to find an integrating factor. So I'm not going to fill everything in just so that we can save some time to make it exact. And then, it's conservative, and then the H is called the integral. So Hamiltonian is a special type of conservative when the mu is 1, the integrating factor is 1. And then we had the phase plane portraits, right, of conservative systems. And really what that is that's taking level curves of a mountain range, projecting it down, and that would be your trail map. If you follow trail, you stay at the same elevation. So you stay at the level curve, and then you're able to draw a saddle, minimizer, maximizer, and then that gives you centers. And then you have to figure out whether it's clockwise or counterclockwise. Bottom line, you could integrate the orbit equation, at least just to even find the H. Bottom line of this time, most autonomous planar systems cannot integrate the orbit equation, but you still want to understand the phase plane portrait. So we're going to go and look at this. Okay. All right. So what I want to do is I want to review the main point of calculus. What were you doing all that calculus for, right? So with calculus, right, the main point is linearization. All right. So linearization is basically this. So, way back in Calc 1, right? Let me see if I could sit a little bit straighter so not as twisted. There you go. Is you have something like this, right? Y equal f of x, single variable calculus, right? And maybe, it's like this. You could even, I'll just draw, here's the x right here, right? And then here's an a. And you take the a, you plug it in, you get an f of a. That's the y, that's the height. So this is the height, right? So then you label the point, you go a, f of a. There you go. And the idea is that this being curvy is hard. And what you want to do is you want to approximate it by somebody that's easy. So you linearize. So the linearization is this. And the idea is that when you look at this, you see when you're nearby, it's almost indistinguishable. Okay. So this guy is y equal L of x, right? And if it's a line, it's mx plus b, right? And then you can see that this could be a very complicated thing. Who knows what it is? It could be something like e to the x, sine of x, blah, 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 ln, x plus 2 pi, x squared plus, e to the x, x, blah, 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 right? So whatever it is, complex, you're going to approximate it by the ultimate simple. And that was the entire point of why you learn y equal mx plus b for 12 years in high school. Okay? So the idea is to take the hard and approximate it by the easy. Now, with us, how do you find the L, right? So you all know that the entire purpose of calculus was to find the derivative, and that is the slope. So the slope of the tangent line is f prime, right? So you need two things. One, you need a point on the line, a f of a, and number two, you need slope. F prime of a. And then, you have your tangent line equation, right? So you do the slope intercept. So you go y minus, f of a. And let me go ahead and now, instead of using a, maybe what I'll do is use x naught. So this will make it a little bit simpler a little bit later. Okay, so let's just relabel everybody. So instead of a, let me go ahead and just do x naught. So here's x naught, right? X naught, when you plug it in, that's f of x naught. And then you have this. Okay, so y minus y1. Equal m times x minus x1, right? That's the slope intercept equation. Y minus y1 minus equal m times f minus m times x minus x1. Okay, then what we're going to do is recopy and take this guy and move it over to the side, except we'll put it first. So we'll go put him here, and then here's the slope. And you guys have seen this. And now, does everybody see this is the original height? And this is slope times the run, right? So for instance, you want to figure out this guy, right? This is the actual f of x, right? And how can you approximate that? Well, this height right here is f of x naught, right? That's the original height. And what you're doing is you can slide up the tangent line to over here, right? And then what you're going to do is you're going to get to here. And so you're going to say, oh, this height is going to approximate the actual original height. And what is the red height? Well, it's the f of x naught, right? Can everybody see that? Everybody can see. And then I'm going to say, this is the original height, right? This is the f of x naught. And then look at this, right? This is the change in the height. So it's rise over run. And you know what rise is, right? So rise over run is equal to slope times the run. And what is the run? Well, if you go over by x right here, then this over here, if you have 0 over here, it's this minus this, right? So this is x minus x naught. That's the run. So the slope is f prime of x naught, and then the run is x minus x naught, right? So the rise that you get over here, that's basically the slope times the run. And this is the run right here, right? So what you're doing is you're going to rise up this much, and you want to get this. So you can see that this is the rise. And so what you're going to get, instead of getting the actual, this is the actual height. Oops, let me get this. The actual height is this, right? What you're going to do is you're going to approximate that by this. And what it is this portion, the original height, plus the height that you get from the rise. Okay, so that's the main idea. Okay. So what you would say is that this guy right here, this is the slope of the tangent line. Okay. And so you would call this guy, this right here, that's the L of X. Oops. Right, that's this L of X. That's the L of X. Okay, so then you would just say, oh yeah, L of X equal this function right here. Okay, so that's what it is. It's the original height plus the slope times the run. Can everybody see that it's y equal mx plus b? Because the mx is this part, and then you distribute and add this, and that will be the b. So ultimately, it's mx plus b. So that's this guy right here. That's what he is. Okay. So then what you're going to do is you're going to say, okay, the original height, the actual f of x, the actual, this is the heart, this is the actual. The actual is this, right? This is the actual right here. That's him. Okay. That is approximated by the easy, right? The hard is approximated by the easy. That's the whole entire idea of calculus, right? You approximate the hard by the easy. Okay, so what I'm going to do now is write it out one more time. Okay, so you guys can see it. But there's a little bit more space. Okay. Okay, so what you have is f of x. The true height is approximated by the original height plus the f of f prime of x naught slope times the run, right? Because this is the L of x right here. This is the L of x. That's who he is. There he is. Okay, so this is this equation of the tangent line. Okay, so that was the main idea of calculus. And what we call this is we call this the linearization of f of x about x naught. That was the point of calculus. Now, you may or may not have taken multivariable, but the idea of multivariable is very similar. You have a z equal f of xy. This is a nonlinear function like above. So z equal f of xy, what's that like? Well, downstairs, right, you have your xy plane. And what you do is you have points down here, and it has an xy, and you plug it in, and then you get a height. And then you have a point here, you get a height. You point down here, plug it in, you get a height. So then what ends up happening is every point downstairs, you plug it in, you get a height, and then maybe something like this. So you see how this is? You get a surface. And then let's pick a special point. So we're going to say this is x naught, y naught. Okay? So what's x naught, y naught? Well, here is the x naught. And here is the y naught right here, right? And so you plug it in, right? Take the x, put this in, put it in, put into the formula, and you get somebody right here. Okay? And who's that point? That point is going to be, you know, x naught. I mean, just so this point right here, he's going to be x naught, y naught, and then you plug it in, you get f of x naught, y naught, right? So that's the point. Okay, so what we want to do is also, you can just imagine this is going to be very complicated. And what we want to do is we want to approximate it by the simple. So we take the hard and we approximate it by the easy. And essentially, you know what's going to happen ahead of time. So, like before, right, the two-dimensional version of a line is a tangent plane, right? Is a plane. So let's see what we're going to do. Okay, so what would happen if you go ahead and you fix y naught? So if you fix y naught, what's going to happen is you're going to lay on top. If you fix the y naught, right, you're going to cut down through the plane. So because you're always going to be at y naught. So you're going to cut down, and what's going to happen, right, is that you're going to cut down through the plane like this. And it's above, right? You're right above here. You're just cutting down through the plane like this. Why not? So then this right here is this right here. This curve is z equal f of x, and you plug in the y naught, right? You plug in this y naught right here. And so now you go back to the previous. Now you're back to the previous example. You're back to single variable calculus. And you know what you can do? You can take the derivative, right? And if you take the derivative, what are you going to get? Well, you'll get the slope of the tangent line above this going in this direction. Okay? And then you know what else you could do? You could fix the x naught. And then you see this plane like this. And what's going to happen is it's going to cut through vertically. And what's going to happen is you're going to cut through like this. So this is going to be above, at this. You're going to cut down, and you're just going to get this. And does everybody see that this is z equal, and you hold the x naught? So z equal f of y. So this is still z equal f of y. That's single variable calculus. So if it's single variable calculus, you go back and say, oh, I can take, a tangent line right here. And you know who his, you're gonna, who his, then you can go ahead and figure out his slope, right? And so when you're taking the slopes now, so looking at this guy, what is his slope? His slope is the derivative of the f with respect to, now over here, it's with respect to x. And for this one right here, this was approximating this guy right here. So the derivative of this line is the derivative of the f with respect to y, because this is the independent variable there, right? And then what you do, of course, is you have to evaluate it at that point. So of course you're going to evaluate it at x naught, y naught, right? And you're going to evaluate this at x naught, y naught. Okay, so now what we did was we basically did everything up here. And now think about, what if you were to go ahead and move off of this x naught, y naught downstairs? So you have x naught, y naught right here. And what if you were to kind of go over here? Okay, so let me just draw this out a little bit further. So can you see then, right? So what you would do is, here is the y value, okay? And let me just go ahead and get this, because we'll get confused, okay? And then this is the x value. Okay, so now you can see that we're going to move to this point, and it's going to be x comma y. All right, so then where is he? He's like, well, he has, so remember, this is the height. This is the original height, right? And the original height is this. That's the coordinate of that point. And now this guy up here, right? His real, height right here, this is x, y, f of x, y. So his true height right here is f of xy. He lays it on that surface, right? And what we're going to do is we're going to approximate the true height by sliding along the tangent plane. So first, what we're going to do is we're going to slide along, let's see, we're going to slide along this tangent line, and then we'll slide, or we can slide along this one, and it's going to be parallel. Okay, and then we slide parallel. First, we slide parallel along the blue, then slide parallel along the pink. Or you could slide along the pink and then slide along the blue. And you're on a tangent plane. So the blue and the pink right there, I'm going to do blue and pink. Basically, what it does is it forms a tangent plane. And what you're doing is you're traveling on that tangent plane to this point right here above the actual, and you're going to get to this. And you can see it's real close, right? It's right there. So the actual is the black right here. So what is the actual height? Let me just draw it again. This is the actual height right here. Okay. And what is the approximated height? The approximated height is going to be this one right here. Okay. Right there. That's the approximated height. So how do we do this? So what we're saying is, how do you go ahead and write down the tangent plane equation? So if you've taken Calc 3, you know that it's going to be like this. So it's actually z minus f of x naught, y naught. And it's going to be equal to the derivative in the direction of the x evaluated with respect to x, evaluated at x naught, y naught, x minus x naught, plus the derivative with respect to y, evaluated at x naught, y naught, y minus y naught. So let me write that again. I'm going to move this over. So this is what this is. So you can see it's very, very similar to what we had before, okay? So does everybody see this is the original height? This is the original height right here, right? So let me just say the original height, this guy, that's this one right here. This is the original height right there, right? And what we're doing, so we're right here. So let me go ahead and make this really dark. So do you see that's the original height right there? Okay, so right here, this is the original height. Okay, and then what you do is then you're going to slide along the blue tangent. So I'll just go ahead and I'll even color code it. So this is slide along the blue, and this is the slope of that's the blue slope. Okay, and that's this. This is slope times the run. Does everybody see what's happening? So you're sliding along this way, right? And so you're traveling along the tangent plane. And so the rise, sometimes you're going downhill. So the rise can be, if it's positive, it's going uphill. If it's negative, it's going downhill. So you're sliding this way, right? You're sliding this way along the tangent line. So you're going to have a certain rise. So this is slope times the run in the x direction, because that's the blue right here is parallel to the x direction. And then what you're going to do is we're going to do the pink, right? Slide in the y direction. And this is the slope times the run in the y direction. Okay, so this is the slope times the run. Okay, so then you're going to slide, after you slide in, let's see, let me grab this. Look, after you slide in this direction, then you're going to slide in this direction, parallel the pink line. Okay, and it also has a rise from sliding along that direction. Okay, so that is actually, does everybody see what this is? So does everybody see that right here? There's a slope right here, so that's AX. Does everybody see there's a slope times this? That's a BY. And then when you go this times this, that's a constant. This times this, that's a constant. Add it to this constant. Does everybody see this? So this is actually z equals c plus ax plus by. And you can see that it's just like mx plus b, right? You have the mx and then you have the b. And so here you have x and y. So this is the slope here, mx, and then mx in the other direction. And then you have this. So this is the equation of a tangent line. Okay. So this is the equation of a tangent plane. All right. So it works very much like the equation of a tangent line. All right. So this is the linearization. Let me just write this, right? So this is the linearization of f of xy about x naught, y naught. Okay, so you could relabel this, of course, as L of xy, right, for linearization. So then you're going to have the original, approximated by the easy. And the easy is the L of xy, which is original height, slide up in the x direction, slope times the run, that gives you the rise, and then slide parallel to the y direction, slope times the run. That's what this is, okay? And this is the original height. So you can see that the true height that we want, right? The true original height is this guy. And what you're going to do is you're going to slide, let's see, I'm going to slide along this, and you slide parallel to this, right? And if you reverse the order, you can slide this way and then slide this way. And then you're right at this point and almost the same height as this, okay? All right, so we have two equations that we're going to do this for. So we did that for the first one. We did it for f of xy, or two functions you're going to do this for, okay? So now you're going to do it for this. You're going to do it for g of xy. So if you had another one, z equal g of xy, maybe you had some other, some other surface like this, right? Over your xy plane. And then here is, x naught. Here is y naught. And you plug this in. And so you're going to get an actual, this is this point up here. So this point, its coordinate, let me see. Its coordinate is going to be x naught, y naught, g of x naught, y naught. Okay, so this is g of x naught, y naught, the original height right here. And what if you slide over here? So I'm going to go ahead and put this guy now over here. And you're at this point now, so I'm going to draw this out a little bit further so you can see this is going to be y. And then you're going to go over here. This is going to be x. So then this is x comma y. So then this is its true value right here. So this is g of xy, right? So I'm going to go ahead, take this guy and move it off to the side so it doesn't run into everything. Okay, so let's just put it right here. All right, so now, so this is the actual g of xy, the actual height. Okay, so you want to approximate it because, and it's curvy, so it's hard. But what are you going to do? So again, you slice in this direction, right? Holding at this point. So you're going to slice in this direction, holding the y naught. You're going to slice vertically like this. You slice down. And when you slice down, you're going to get this like this, right? You're going to get this curve right there. So let me go ahead and just clean that up. So it's just, this is like this, right? So this is when you hold z equal g and you have of x. And you can see you're going to hold the y naught. And he has his own tangent line, right? And that's slope of that guy, the slope of that guy is partial of g with respect to, and you can see x, and you're going to evaluate it x naught, y naught. Then over here, what you're going to do is you're going to cut straight down, right? And you're going to cut straight down here through this. Sorry, I'm just going to draw this. So you're going to cut straight down, right? You're going to cut straight down. And you're going to get this, right? So there's going to be a curve. Let me draw it nicer, right? There's going to be a curve like this, right? Where you cut straight down like this, where you hold the x naught. So this guy is going to be z equal g of x naught y. But again, you can see that this guy is a function of one variable, and here is the tangent line right here, and its slope is partial of g with respect to y, because this is what you have, partial of g with respect to y, x naught, y naught. And those two form, right? They form a tangent plane that approximates the curve, right, at that point, okay? And so what you're going to do is you're going to slide this way, and then you're going to slide, we just need to go this way, and then you're just going to get right above this. It's going to hit right here, and there it is. Okay, so that's the height that you're going to get. Okay, so what you're going to do is you're going to slide, you know, and what is the run? Can you see what the run is? So here, right here, this distance is this subtract this. So this distance is y minus y naught. This distance is x minus x naught. So this distance right here is x minus x naught. So that's the run, okay? So above there, you're going to slide in the blue direction, and then you're going to slide in the pink direction, and then you're going to get to right above here. In fact, it's really close, right? So close that it's almost just right there. It's just right there, okay? So you're going to have the true height, and you're going to approximate by the original height, which is the original height right here at the point of tangency. And you're going to have partial of g with respect to x. This is the slope. Slide in the x direction times the run. Partial of g with respect to y, x naught, y naught, slope times the run. Okay, so you have two of them. What are the two things from? Well, remember what we were doing, right? We're going to be, you know, what we're really doing is we're looking at dx dt, dy dt. This is our system, right? And this was the f, and this was the g. Okay? Now, I want to do a teeny quick review about what it means to change variables. Okay, so we're going to do a quickie, teeny review. So, let's see. So if I have something like this, okay, so I'm going to just draw this. And you all know, here's my XY plane. And this is 0, 0. And let's say this is X naught, and let's say this is Y naught, like so. Or you know what? I'm gonna do it with actual numbers, because then it'll be easier for you guys to see. So let's say, let's do this is going to be 1, 2. All right, 3, 4, 5. And how about 1, 2, 3, 4, like this, and maybe one more, 5. There we go. And let's do 3 right here. Okay, so you see this is the point 2, 3. Okay, can you guys see that I could actually do another coordinate system, and I'm going to call this guy x tilde y tilde. Now, in this other coordinate system, right, now what I'm going to do is I'm going to go ahead and maybe look at this point right here. Now, we have a black coordinate system, xy, and a blue coordinate system, xy tilde, x tilde, y tilde. Can somebody tell me what is the coordinate of this point in the black system? What is the coordinate using black?
5, 4.
Yes, 5 comma 4. Okay, so that's the xy. Now let's do it in this system, x tilde, y tilde. Can somebody tell me what is the coordinate with respect to the blue?
3, 1.
Yeah, 3, 1. Does everybody see that? Okay. And remember, who is the new origin? So the new origin for the blue, the old origin was 0, 0. The blue origin in terms of the black is what?
2, 3.
3, right? So can everybody see how it works? So basically, what you want to do is you want to change from black to blue. So if you had, for instance, anybody who was blue, right? How would you change it from the black coordinate? Just looking at this above. What's the relationship?
X plus 2.
Almost. X minus 2, right? So does everybody see if you put in the 5 and go 5 minus 2, you're going to get the 3? So let's do that again. How about y tilde? You want to write it in terms of the black. What would it be?
Y plus 3.
Y.
Minus 3.
Does everybody see that you would put in the 4 minus 3 and then you would get the 1? Okay, so does everybody see how it works? So to get the tilde, right, you go black minus 2, y, and then black y minus 3. So you're subtracting the new origin. Okay, so does everybody see this? So this is the change of variable formula. And you could go the other way. If you were doing black and you started off with a new one, then what would you do? This would be x tilde
Plus 2.
plus 2, right? And then y would be the new one plus 2. Okay, so I'm going to just do it in general now.
Isn't
Okay,
it plus 3?
a 3. Thank you. Yeah, thank you. Okay, so what I'm going to do now is let me just kind of get this out of the way. Okay, let's do this again. Okay, so if I had somebody like this, right? And I said, okay, here's x naught and this is y naught. And this is the new origin. The new origin is going to be the new origin is going to be x naught, y naught in terms of the black. And you're going to have another coordinate system right here. You can call it x tilde and y tilde. All right. And then you were going to try to figure out this. Okay. So then this is going to have black coordinates, right? This guy right here will have black coordinates. And it's also going to have blue coordinates, tilde coordinates. So can you guys tell me what is the change of variables formula? Starting from, if I want to find the blue, what would the change of variables formula be?
So x tilde equals x minus x naught.
Perfect. And what else?
Y tilde equals y minus y naught.
Exactly. And then if you were to start off with the x tilde and you were trying to find the black, that would be
X
x
tilde plus
tilde
x naught.
plus x naught, right? And then the other way would be y tilde plus y naught. Now, just want to say something. Back in high school and in calculus, when we went over here and we were doing this thing right here, Does everybody remember this is y minus y1 equals m times x minus x1. And some teachers would say, you can leave, you're trying to find the tangent line, the equation of the tangent line. And some of them would say, okay, you could leave it like this. But other people would say, no, I want you to rewrite it as y equal mx plus b. Okay. But the ones who said, no, you can just leave it like this. Can you guys see that this is the new? This is like, does everybody see that this is the x naught and the y naught? And does everybody see then y minus y naught right here? This is the y tilde. And then this over here, this is still going to be the same. This is the slope. And does everybody see over here, this is the x tilde? So do you see it's always y equal mx? That's because when you do it this way, what you're really doing is over here, you're drawing a new coordinate system. Does everybody get it? This is the x tilde, this is the y tilde. And so your tangent line goes through the origin. So that's why it's y equal mx. Does everybody get that? So you could have, let me just make it nicer, oops. So if you had actually drawn, let me just use lighter blue right here. If you had drawn another coordinate system right here, and this is x tilde and y tilde, then do you see instead of y equal mx plus b, you could have written y tilde equal the same m because it's the derivative. So it's going to be the same m, x tilde. That's what was going on right there. Okay. So now what I want to do is we're going to review this because this is what we want to really work with. We want to look at this guy, right? So we want first, I told you when we're working with this, we always find the stationary point first. So we're going to assume that that guy's a stationary solution, right? And how did you get it? You get it by you set this equal to 0 because you want the constant forever solution, right? You set this equal to 0 because you want the constant forever solution. I told you guys that, right? So then if this is a stationary thing, and then you solve. And get this. But then what that means is if you stick it in here, you're going to get, does everybody see what that means? That means that if you stick it in here, that's going to be equal to 0. And if you stick it in here, that's going to be equal to 0, right? Does everybody see that? If x naught, y naught is a stationary solution, then you set this equal to 0, you solve, and that's how you get in the first place. So then by concept of what stationary solution is, when you plug it in, right? So that you get a constant solution, right? You get, dx dt, so x is constant, y is constant, right? That's the idea. So this is what it means to say that x naught, y naught is a stationary solution. Okay? Let's put it all together. So we have this. This is our system. That's nonlinear. It's the f and the x look like this, right? And that's dx dt, and that's y dy dt. So what we're going to do is we're going to approximate this, right? That's hard by the easy, right? So what we're going to do is we're going to go original height, slide along the tangent line in the x direction. And we're going to go ahead and we're going to approximate it. We're going to linearize it about the stationary solution. That's slope times the run. And then we're going to slide in the other direction. We're going to slide in the y direction on that tangent line. Everybody got it? Slope times the run, and that gives you the rise in that direction. So you get the rise in the x direction and the rise in the y direction. And sometimes you're going downhill. Rise can be plus or minus. And you know what? Let me go ahead and get the light out of my eyes. So I'll be right back. Just 1 second. Okay. So we've got this. And now we're going to go ahead and approximate this, right? And remember, it is actually easier, right? Because this is actually a tangent plane. And this might be, you can see it's actually way easier, right? All right. So then this is the original height plus the slope in one direction times the run. And then over here, you have your original height, slope times the run. Everybody got that? And now what you're going to do is, that was a stationary solution. This is 0. And after you plug this in, right, this is your m in the y direction, and these are constants, right? And look at this. So what we could do is, let's change variables, right? This will be x tilde, y tilde, x tilde, y tilde. These are constants, because once you plug in the x naught, y naught, you get numbers there. So consider this system right here. What we're going to do is we're going to look at the dx tilde dt, dy tilde dt. Okay? And remember, who are we looking at? It's this. So we're going to use this, right? So I'm just going to say this is off to the side. This is what we're assuming right there. Okay? And this is going to be equal to, and everybody can see, right? This is the matrix. This is a number right here. You plug in x naught, y naught. This is slope in the other direction. Of course, you have to evaluate it at the point to get the actual slope. This is for the other one. Slope in the x direction. Slope sliding along the tangent plane in the y direction, right? And then over here, look at this. X tilde, y tilde. Look at that. Remember, these guys are all constants. And now, I think what I'll do is I'll just kind of make this a little bit smaller, like this, okay? Does everybody see that this is, I'm going to write, does everybody see? I'm going to go like this. So I'm going to go like this, and I'm going to go like this, all right? And then I'm going to go like that. So this guy is going to be, does everybody see? This is going to be x tilde, y tilde. And then remember, I can leave off the of t. A lot of times, remember, we just leave off the of t, right? So we're going to have the tilde system. Okay, one more time. This guy is not this guy, right? This guy is both of them. And this one is the first coordinate. Okay, so now that we've established that, let's go back to this. This is dx tilde dt equal, and this is ax tilde. And what you have is, this is a linear system. This is from chapter 7. I told you need to memorize the 20 linear phase plane portraits. This approximates the original. And the original is this. It approximates this. And the conversion right here is going to be right here. I'm just going to put it right here just to remind you. Okay. And so what would happen is the actual solution is going to be this, right? It's going to be in black. Right? And that's this, x of t, y of t. Remember, this is not this, right? This is both of them. This is for the nonlinear system. And it is going to be approximated, that's the hard, it's going to be approximated by the easy. And it's going to be approximated by, and look how it works, right? So we want to get this, so we're going to look at this, which you know how to do from chapter 7. So you're going to get these guys right here, right? So then you'll take these guys and you stick them in here, right? So in other words, what you're going to do is you're going to have x naught plus the x tilde of t, and then you're going to get y naught plus the y tilde of t. Okay, so you're going to solve this, right? And get, so solve, get x tilde of t, y tilde of t. Get that solution. Get the solution for the linear. All right. And then once you have that, if you stick it here, do you see that that is going to approximate the nonlinear? Okay, so I'm just going to say, so this is the solution to or of the linear system. Okay.
Is that a first order Taylor expansion we did in the previous?
Mm-hmm. Sorry?
No, I was asking if it was a first order Taylor expansion that we did.
Yes, that's what it is.
Oh,
The tangent, yeah, the tangent plane is basically the first two, the first two, the first part of the Taylor expansion. That is what a linear expansion is. And then when you add the next, that's the quadratic, approximation. Then when you add the next term, that's the cubic. That's what a Taylor series is. The Taylor polynomials are, polynomial approximation to your original. So you start off with your linear, which is first order, and then you have your quadratic, then you have your cubic, then you have your quartic, and so on and so forth. All right.
Oh, just the approximation of the nonlinear function by the tangent plane.
Yes. Yes.
Okay.
Okay. The linear system above is called the linearization of the original system. This is the original system. This is the linearization. Okay. And you say that that is all about x naught, y naught, and you want it, the x naught, y naught, to be a stationary solution. Okay, so this is going to be a stationary point. Because we want this part to be equal to 0. Okay. And the matrix A is called the Jacobian of the F. So who is the F? The F, right? Remember that who the F is, right? The F is actually f of xy, and don't forget, he's actually f of xy, g of xy. So that's this, okay? So the Jacobian matrix of that, let me write that down for you. That is, again, you write it like this. You just go like that. So that's the Jacobian matrix. When you evaluate it at a point, you can stick it like this. And the way you write it, the Jacobian matrix is like this, right? So you just go partial of f with respect to x, evaluated at x naught, y naught. Partial of f with respect to y, evaluated at x naught, y naught. Partial of g with respect to x, x naught, y naught, partial of g with respect to y, x naught, y naught. Okay, so this is the Jacobian matrix. I want to say something. Don't confuse it with a Hessian. Just think Hessian has two S's. So 2, just remember that you write a little 2 here, right? And that guy is this. The Hessian is, and you can evaluate it also at a stationary solution, right? That guy is different. Hessian is you take the second derivative, take the derivative with respect to x, then take the derivative with respect to x. First take the derivative with respect to x, then take the derivative with respect to y. Take the derivative with respect to y, take the derivative with respect to x, take the derivative with respect to y, then take the derivative with respect to y. Remember, we used to write this, you can write like this, right? You go like this, right? So this is taking the derivative. Okay, you start off with the h. Notice that you're going to take the derivative with respect to x, right? And then you're going to take the derivative with respect to y. So when you do go like that, then you write the del square, right? So this is how you write it. So that's this one right here, and so on and so forth, okay? But it's just simpler to write it this way. So notice Hessian, just think 2 S's, 2 derivatives. Jacobian is derivative of the first matrix of the first derivatives. Okay. So remember from linear algebra that the invertibility of a determinant matches the invertibility of the matrix. If the determinant is not invertible, the matrix is not invertible, right? So just kind of off to the side, determinant of A. If it's not invertible, matrix is not invertible. And what is the one number that is not invertible?
0.
That's right. So if you have that, A is not invertible. And so that means if it is not 0, then A is invertible. And of your 20 that you're supposed to memorize, 15 of them were invertible, and those are the most important ones. Okay. Oh, and then over here, just to say you would evaluate it. You would evaluate it at this after you plug this in, right? So you would take this and just you can plug in the x naught, y naught. Okay. That's because of this. Okay. So now we're looking at the phase plane portrait of our actual original system. This is the original system. Okay. It's going to be near, this guy is going to be near a stationary point, and the stationary point is x naught, y naught. Let me just kind of make this all smaller. Okay, so this guy. It's going to look like, and of course, only nearby, x naught, y naught. It's going to look like this guy. Dx tilde dt, dy tilde dt equal partial of f with respect to x. Evaluate at x naught, y naught. Partial f, the slope in the y direction at that point, the slope of the x direction for the second at that point, the slope here at that point. And then x tilde, y tilde, right? And this, what I'll do is, let me go ahead, make this a little bit smaller. And let's take a look over here. This is dx tilde dt equal ax tilde. Okay. This is the linearized system, and you guys know how to draw those. Those are the 15 that you have to have memorized. And it works when the determinant of the A does not equal 0. Okay? So the phase plane portrait of near the station of the original near a stationary solution is going to look like the phase plane portrait near the origin of the linearized system, and we have a new origin, right? The new origin is going to be at x naught, y naught. That's the main idea. So we're putting everything all together now. And so hopefully, remember, so let me remind you, who is the A again? The A is the Jacobian, evaluated at x naught, y naught. That guy. There's 15 of these that you need to know. That's the A. Okay. So remember when you had two real eigenvalues, right? So you could have both positive, right? And then you have a nodal source. This is in the linearized system. Maybe what I'll do is I'll write this in blue because it's linearized. Okay. And you can have both negative. Remember, nodal sink is how you would characterize it. And remember, one positive, one negative. This is a saddle. Okay, but the original system, so this is all at x naught, y naught, right? So this is at the origin, at the origin. But remember, we have a new origin. The new origin is x naught, y naught. Okay, so then you're going to have everything here. They're all going to look similar. So what's going to happen is in your original system nearby, they're going to look similar. Near the x naught, y naught, which is your, which is the origin on this side. Okay, so that's the idea. Now, one of the things you want to remember is you want to be able to write down your eigenvector line. Okay, so if you have an eigenvector, v, okay, I'll write it as u naught, v naught. So, assuming that the first one is not equal to 0, you know that the slope, right? The slope is going to be, this is like change in y, this is change in x. So you're going to have change in y over change in x. Okay? So then your eigenvector line is going to be, and let me go ahead. Let me make everybody blue here. Your eigenvector line is going to be y tilde equal m times x tilde, and the m is v naught over u naught, right? Because the bottom, if we assume that, okay, so it's going to be this. Can you see that you would also have the orbits going over here? Orbits are going to be tangent to the line y minus y naught equal m v naught over u naught x minus x naught. Because this is the y tilde and this is the x tilde. Okay, so you're writing the same thing down. So you write it like this, right? And this is going through the point x naught, y naught. Okay? So that is how it works for two real eigenvalues. Let's look at what happens with one real eigenvalue. So let's assume, for instance, let's see. So this one, let's do multiplicity 1. Okay, so that one would be, for instance, you have one real eigenvalue, right? And then this would be negative, right? And so this would be a twist sink. So this, we did it. And if it's positive, this is a twist source. So please look at chapter 7 stuff. And then you have to figure out if it's counterclockwise or clockwise. Counterclockwise or clockwise. Okay, so you want to write it down. And then similarly over here, and I should go ahead and make this blue. Okay, so this is going to be the linearized system. Then here, what you have is that the orbits are tangent also to the line through x naught, y naught, okay? And again, in the direction of the linearized system. Okay, and the counterclockwise and the clockwise will match. Let's look at one real eigenvalue, multiplicity 2. So when you have this, right, what happens is that you're going to have negative, you have positive, right? And this will be a radial sink. And this is going to be a radial source. All right. So then again, in a similar way, what's going to happen over here is that every half line, so these are the ones that we care about, where the determinant, let me just say that again, that the determinant of the Jacobian is not equal to 0. Okay, so every half line radiating from the x naught, y naught, which is our new origin on the other side, has an orbit tangent to it. Let's say you don't have any real eigenvalues. Then let's say your lambda equals a plus or minus ib. Okay, so then if the a is less than 0, remember what that was? Let me go ahead and write it down in blue. When it was less than 0, then you had a spiral sink. You have to determine clockwise or counterclockwise. When it's greater than 0, you have a spiral source. You want to determine clockwise or counterclockwise. And then what's going to happen is that this is going to just be very similar. You're going to have something like a spiral sink, like a spiral source, and the clockwise, the counterclockwise will match. If your origin is a center in the linearized system, one of the things you have to do is you must check that the original system so that is when the a equals 0, you have pure imaginary, that it is conservative, because you need it to be conservative for it to actually match. Then if it's not conservative, this might not hold. Okay, then you're going to get a center over here. And that's going to be similar. And then this is going to match. Okay. And then if the determinant is not equal to 0, so remember what these were. This was your linear sink, linear source. You have a 0. You have parallel shears. Okay. These guys, the eigenvalues, you'll have an eigenvalue 0. Okay. And what ends up happening is at least one line of all stationary solutions. So they're not, or stationary points, so they're not isolated. Okay. So then you won't be able to figure out what it looks like over here. Okay. So you only have 15 of these. So there are 15. So these are the ones that you can do. Okay. And once you have this, right, you then worry about stability. So you always have to do a stability analysis of your stationary points. So real quick, it's stable if every solution starting near it stays near it, otherwise it's unstable. It is attracting if every solution starts near it, but not at it, approaches it as you run time forward, right? And then it's repelling. If you start near it, it has to be every solution, okay? Again, as you run time forward. Okay, so notice that if it's attracting, that automatically means stable. And if it's repelling, it automatically means unstable, but it's not the other way around. Okay, so for instance, if you have a center and you're circling nearby, you stay nearby, but that's not attracting. So this is not necessarily the case. Okay, so when you do this, I'm just going to say these are going to match very much. So, oops. So whatever is happening in the linearized system for your 15, the same is going to be this. It's going to be the same for your original. But one thing you want to do, so I'm going to skip writing it all down, okay? But one thing I just want to say, remember that when you were doing for your conservative system, when you have this, an integral with non-degenerate critical points, this means that all stationary solutions are going to be saddles or centers. So if you have somebody that's not, so, if you do a linearization and it shows, stationary solutions, or stationary points, let me just say, that are not saddles or center, then you know automatically system is not conservative and does not have an integral H or Hamiltonian, obviously. Okay, so if there's somebody besides a saddle or center, it's automatically not conservative. Okay, but if all stationary solutions are saddles and centers, it may not be conservative. It's possible it might not be, okay? So you must check if conservative. It's never going to be harder than Hamiltonian, so remember this. This was the check, right? This was the check. Now, remember, technically, you multiply through by mu, for the bigger case, but we're not going to make it harder than that, okay? So you need to check that it's conservative, and then the original. Then the original system will look like. The linearization near the stationary points. So that's the one thing. You do have to check that it's conservative, okay, if you have saddles and centers. Okay, so we're ready to do a specific example, okay? So let's go back and do this guy again. We did it again last time. So this was Hamiltonian, but we're going to do it from a different point of view. Last time, we did the Hessian. Found H. We did an orbit equation. And then we found, and then showed it was exact. And then Hamiltonian. We found H. And then found the Hessian. Okay. This time, what we're going to do is we're going to do it from the point of view of the Jacobian. You can do more because when you have this situation, you can only do saddles and centers. But if it's not saddle or center, then you usually, obviously, you want to do Jacobian. But the other thing about the Jacobian is it gives you more information. It makes the picture look nicer, okay? If you use, so you may want to do this, you find the Hessian, right? And do all of that if it's conservative. But you can use the Jacobian to get more detail, to get the eigenvector lines. Okay, so let's go ahead and do this one. So remember, it's always good to label. Who's the F, who's the G? Then remember, you set this equal, you always find your stationary solutions first. So stationary solutions. And we already did it. Okay, so the stationary points are 0, 0. And do you remember we had -2, 0 and 2, 0? Those were the stationary points. Now what you want to do is you want to go ahead and write down the F, right? Now, who is the F? Now, remember, X is XY. So remember what this really is. This is F of XY, and this is the X right here, and G of XY. Okay? And what we're going to do is, let me go ahead and write that down. This is equal to, right, the Y. This is the 4x minus x cubed. Let's write down the Jacobian. The Jacobian is first partial of this. In fact, I'll make it bold so that you can see this, okay? So we're going to go like this. And what we're going to do is we're going to do partial of f with respect to x, partial of f with respect to y, partial of g with respect to x, partial of g with respect to y. Okay, and so let's look at this guy. What is the derivative of that with respect to x? What's the derivative of that guy with respect to x?
0.
0. What is the derivative of this with respect to y?
1.
Good. Now, focus your eyes here. What is the derivative with respect to x?
4 minus x squared.
3x squared, right?
X squared.
Okay. What is the derivative with respect to y?
0.
Good. That's your Jacobian matrix. Okay. That's the Jacobian matrix. Now, what you want to do is you go ahead and you do each thing. So we start off, and I'm going to go ahead and do the harder one. All right. Because sometimes it gets the easier one is a little too easy. And it's so easy that it becomes hard. Okay. So instead of doing 0, 0, I'm going to do 2, 0. Okay. So I'm going to do this one first. So we're going to find the Jacobian and you plug it in. Okay, so let me go ahead. I'm going to just kind of clean up everybody here, okay? Oops. Write this here. I'll put the Jacobian right here so that you can see it. It's like right here. Okay. By the way, one more time, before we get started, does everybody see now? Let me put this over here. Does everybody see, after you find all of this whole entire thing can be written as dx dt equal f of x, right? Because this part is this, and this x is this and this. Does everybody see that? So it looks like it's something from part 1. And what we're going to do is we're going to approximate this by dx tilde dt equal ax tilde, where the a is going to be this guy evaluated at the stationary point. Okay, so we're going to plug this in, and we plug it in. So this is going to go right here, and it turns out that everybody is, this is just like that, and then that is 12. So 4 minus 12 is minus 8, and then this is 0. This guy is our A, okay, for this point right here. And then what we do is we say, okay, do you see what we're really doing? We're going to take the original system. We take the original system. That original system is dx dt equal f of x. And it's going to be approximated by this system, by the linearized system. And that guy, this whole thing is going to be approximated by dx tilde dt equal ax tilde. Everybody got that? So looking, we're going to have, this is the A of the new system. Now, with the A of the new system, right, what we can do is we can do the characteristic equation. Okay, so let's just go ahead. What is the characteristic equation? P of z equal z squared. And what is the trace?
Plus 8.
The trace
0.
is what?
Oh, sorry.
0.
Yeah, minus the trace,
Plus-
which is 0. And then what else? Plus the determinant.
Plus 8.
So it'd be minus 8.
I'm saying minus
Wait, no, yeah, you're right. Sorry.
Minus 8 or plus 8?
plus 8.
Yeah, because you're going to subtract that, right? Does everybody see that's the characteristic equation? So the characteristic equation is this. So does everybody see that the eigenvalues are going to be what? Plus or minus?
Plus or
I,
minus
root-
I square root of 8.
Which is
Plus or
2 roots.
minus 2 root 2i.
Right. 2 root 2i.
Sorry, plus or minus 2 square root 2i. Yeah.
Yeah. 2 root 2i. Exactly. All right, so when you have that and it's pure imaginary, then you have a center. The moment you have a center, right, you know that you have to check the original is conservative. So you quickly check it. You go partial of f with respect to x plus partial of g with respect to y. So we go back here. What is the derivative of this with respect to x? 0. What is the derivative of that with respect to y? 0. Okay, so we need it to be conservative so that our linearized system will resemble the original. So this is all set. Okay, and so now, right, so this is this means Hamiltonian. And if it's Hamiltonian, it's automatically conservative. Okay, so now what we're going to do is we're going to say, okay, we need to figure out, is it clockwise or counterclockwise? So what we're going to do is we go dx dt. So this is this. We write down the a. The a is 0, 1, minus 8, 0, and x. So this is actually x tilde. So in the tilde system, right here, okay, this is the tilde system. So right here, let's check and let's plug in 1, 0. Okay, so we plug in 1, 0. So if you plug in 1, 0, what are you going to get? You are going to get
0.
0 and minus 8. And that is going to be your tangent right there. So in the tilde system, you're going to have a 0, minus 8. This is your tangent right here. That's this guy. So if you have something going like this, and that's your tangent, and your curve is going like this, is this clockwise or is this counterclockwise?
Clockwise.
So it's clockwise. It's a clockwise center. That's how you can tell. So that means your original is going to resemble this, but remember the new origin, who's where the new origin is? This is where the new origin is going to be, at the stationary. And then you do a stability analysis. When you have a center and you start nearby, you're going to stay nearby because you're just circling around. So if you're orbiting right around there, it's going to be stable. And it's not going to repel. And it's not going to attract. So you always need to do a stability analysis.
Excuse me, Professor. Could you also use the shortcut of using A1, 2?
Yes, absolutely. You can memorize that.
Okay.
I'm just justifying it. Okay. Because sometimes you're going to use one or the other, because sometimes it doesn't work. So you might want to use like 0, 1, or you want to use some other point. Okay. But yes, you can always use this. I don't mind if you do that. Okay. So now let's go ahead and do the next one. Okay. So let's just go ahead and we're going to do -2, 0. So we take this right here and we take this and we plug it in to everybody here. And you can see that it turns out that you're going to get the same thing, but you're going to have a new origin. The new origin is -2, 0. Okay. So what you're doing is you're taking your original system, you're going to approximate it by this. It turns out the same linearized system at the new origin. And then all of this is going to be the same. All of this is actually the same, right? Because it's the same A. So I can go ahead and I'll just duplicate it. It's fine. So those were the harder ones. And now let's do the easier one. The easiest is so easy that it's hard. That's why I saved it for last. Let's just do the origin. That was this one right here. Okay. So because it's already at the origin. So you're doing this, you're actually approximating this by this. Okay, so let's plug in the 0. When we plug in the 0, we get 0, 1, 4, 0. So let's just put that one. 0, 1, 4, 0. And this is your A. Okay. So let's figure out the characteristic equation. So characteristic equation is P of Z, Z squared. What is the trace?
-1
And what is the determinant?
plus or minus. Right.
What's the determinant?
I see.
-4.
That's -4.
So then you have Z plus 2 and Z minus 2. And so when you set it equal to 0, what are your eigenvalues?
2 and -2.
Yes. And now what you would say is you have 2 eigenvalues that are real, positive, and negative. So you're going to have a saddle. Okay. And now you want to figure out using Cayley-Hamilton, what are the eigenvectors? And remember Cayley-Hamilton, characteristic polynomial annihilates the matrix. P of A equal to 0 matrix. So then you say A plus 2i, A minus 2i equal the 0 matrix. And you copy down the A, 0, 1, 4, 0, space. 0, 1, 4, 0, space, equal to 0 matrix. Remember, the plus 2 is actually subtract a -2. Remember that subtracting 2, remember that that's the positive one. And what you should get is you should get something that looks funny, because this is created or chosen so that the determinant equals 0. And you only need to write it once because you can imagine it turned around, because you can imagine these guys turned around in its opposite order. But what you have now is you have this A, right? And you have the plus 2i, and that's the first one. So he's this one, and he is acting on this to give you the 0, and he's also acting on this to give you 0. So can somebody tell me then, that being the case, if your lambda equal -2, because this is minus minus 2, what is a good eigenvector?
-1, 2.
I'm going to go ahead and choose 1. So please, guys, always make the first one positive if you can. Make it more simple, okay? So make the first one positive and make it and you want to reduce. Now, imagine that you have this guy right here, this one out in front, because we could have written it in an opposite order. So then you would imagine this being here, but it's actually on this side, right? And it's acting on this guy to give you the 0. It's acting on this guy to give you this 0. So that being the case, if lambda, blue lambda, is equal to +2, what is a good eigenvector for that one?
1, 2.
Yeah. And you can always write it this way: -2, 1, -2. And then over here, you would write 2, 1, 2, right? Okay. Now, having done that, let me go ahead and move this up so that we have more space. Okay, so let's see. these guys right here. There we go. These guys right here, looking at this, we want to write down the eigenvector line. So does everybody see that with this one, the eigenvector line is this? It is y tilde, let me reuse it this, y tilde equal m. So this is changing x, this is changing y. So you can see that this is the slope, and this is x tilde. And can you see the eigenvector line? That's in the tilde system. But if you had this, if these had been other numbers, like if that had been a 3 and that had been a 5, can you see that your original one would be y minus 5 equal minus 2 times x minus 3? So you would go ahead and go y minus y naught equal m times x minus x naught, okay? But because this one was just basically 0, 0, then it's going to be y minus 0 equal minus 2 times x minus 0, right? And that's just y equal minus 2x. Similarly, over here, the eigenvector line, so this is the eigenvector. Similarly, over here, you have this, and this is going to be change in x, change in y. So this is 2x tilde. So then you would go ahead and say y minus 0 equal 2 times x minus 0. But if that had been something besides 0, this is the equation of the eigenvector line. Okay? And now what we have is, we have the saddle. We need to do stability analysis. So in the center, you have one direction coming in and most of them going out. So it's not stable. It's not repelling because there's one direction where you go in, but it's certainly not attracting. Okay. And now we've done our stability analysis. And now we're finally ready to draw our thing. And this time we actually have a lot more detail for our picture. So with this right here, you can now just draw it. This is your phase plane portrait. X, Y. So you know that there was a 0, 0. You know there was a 2, 0. You should label all of these. And you know there was a minus 2, 0. And at 0, 0, what you should do is you should draw your saddle. So I'm going to draw this. So there was the red line. And notice that V is 1, negative 2. So if you go over 1, down 2, the slope is like this. Okay? So you'll draw the slope like this. So this is your eigenvector line. So you draw it like this. The slope is like this. Okay? And it is negative. So do the arrows point in or do they point out?
Point in.
Point in because it's negative and you come in, right? E to the
Oh,
negative.
yeah.
So it comes in like this. Does it actually reach the origin?
No.
No, because of uniqueness, right? And now let's go ahead and look at this. This is the eigenvector you go over 1 up to. So you can see that now you can see, oh, this is what the eigenvector. Now you can see this is a little bit better. And is it going to point in or is it going to point out?
Point out.
Pointing out. Okay. And now you can see, hey, wait, look, does everybody see that this is what it's going to look like? Nearby, you can draw the arrows, right? As you run time forward, you approach the blue. As you run time backward, you approach the red. The arrows should be, as you run time forward, you approach the blue. As you run time backward, you approach the red. Don't draw it like this, right? Because you're actually approaching the asymptotes. There we go. Okay, runtime forward, you approach the blue. Runtime backward, you approach the red. Then over here, you see that you have centers because you have pure eigenvalue, imaginary. The eigenvalue is imaginary. So you're going to have these centers, and we said clockwise for both of them. Notice, clockwise, right? Clockwise right here. We said clockwise. So that is, hard to draw, but you can just say, well, it's going to kind of go like this. But now you kind of have more of an idea. Oh, it's kind of tall looking clockwise, right? And it's like this. So you have several of those. You can draw several of those. And now you can see, oh, it's like this. Right? Because what's going to happen is you're going to approach that. And now we have just kind of a little bit clear, some more clarity than we did last time. So it's nice to do Jacobian, right? Get a little bit more clarity. Clockwise, make sure it's clockwise. Okay, so then let's see. So what's happening? So as you go out, it's going to be pulled over here, right? And what's going to happen is it's going to come around, right? And what's going to happen is it's going to be pulled in this way. Right? And same here. So this is going to come around. That wasn't very nice, but you get the idea. Okay, but then over here, you can see what's happening here. Oh yeah, it's like this. You can see the direction. And the Jacobian is really, really great because if you have, a lot more other things than ones, if it's not centers or saddles, once you know the 20 or the 15, actually, then you have a really good picture. So does everybody see? This is your face plane portrait. Okay. So on the video for this lecture, there's another problem right here. This is the other one that we did. And you'll see that one has, a spiral. That one has a nodal source, and then it has a saddle. So typically you'll have a couple of them. And then there's also a spiral sink. So it has all sorts of things in that one. So this will have 4 of them. They're all really different. And so go ahead, watch the video, do this before next Wednesday. Okay. So this is the main idea for the course. And then after the test, we're going to put a story to the whole thing and interpret it in the context of a cool story. Okay. So this was kind of what it was all about. So it was really great that you all lasted this long in all your courses, Calc 1, Calc 2, Calc 3, and then differential equations, and, really got an idea of how we can, predict stuff. So we'll have a story where we can predict stuff. Okay. So I will stop right here. Thank you for staying. I just thought it would be very nice for you to see a full, exam.